In the, in the previous class, we have derived a relation between absolute refractive index of two medium, that is n2 by n1 equals to sine I by r, where, or this can be written as n1 sine I equals to n2 sine r, where n1 is the absolute refractive index of first medium and n2 is the absolute refractive index of second medium. I is the angle of incidence and r is the angle of refraction. Now, if there are several boundary and light passes through this boundary, then a relation can be derived. Uh, uh, mm, in angle of incidence and angle of emergence. Let in this figure, this represents medium 1, this represents medium 2, this represents medium 3, and this is again medium 1. That is, after passing to two different medium, light comes out again in the same medium. Then there can be a relation can be derived between showing the angle of incidence I and angle of emergence R double dash. Here, when light passes through first medium to second medium, this is the angle of incidence and this is the angle of refraction. Now for this medium, in the second boundary, this is the angle of incidence and this is the angle of refraction. And again for the third boundary, here this shows the angle of refraction, angle of incidence, and this is angle of refraction. And finally, because it comes out of the same medium, so this is the angle of emergence. So we can apply our formula to give to derive a relation between these mediums. For example, in the first boundary, at boundary 1, this is the boundary 1, n1 sine, we can use this formula, n1 sine I equals to n2 sine r. So n1 sine I equals to n2 sine r, and this is the equation 1. But at boundary 2, here the angle of incidence is r, because this line and this line is parallel, so angle of this angle will be equal to this angle. And now at boundary 2, this angle is behaving as a angle of incidence, and this will be the angle of refraction for this boundary. So for this boundary we can write using above relation, n2 sine I, because this medium is n2, refractive index of this medium, n2 sine r equals to n3 sine r dash. Again for the third boundary, here due to because this line is parallel to this line, so this angle will be equal to this angle, and for third boundary, and r dash will be the incidence angle for third boundary, and this will be the angle of refraction. So we can use above relation at boundary 3, n3 sine r dash equals to n1 sine r double dash, because refractive index of this medium is n1. Now from this equation 1, 2 and 3, we can write n1 sine I equals to n2 sine r equals to n3 sine r dash equals to n1 sine r double dash. Now from first and the last term, n1 sine I equals to n1 sine r double dash. This implies sine I equals to sine r double dash. So this implies I equals to r double dash. That is, angle of incidence is equal to the angle of emergence. Again, we have relation n to 1, that is refractive index of 2 with respect to 1, given as n2 by n1, where n2 and n1 are the absolute refractive index of medium 2 and 1. And we know that absolute refractive index is with respect to air or vacuum. Again, n23 equals to n2 by n3, that is refractive index of 2 with respect to 3, and n31 is the refractive index of 3 with respect to 1, equals to n3 by n1. So multiplying n23 into n31, we have n2 by n3 into n3 by n1. We get n2 by n1 equals to n21. So this is also a relation which is showing. Now lateral shift. If a ray passes through uh, a medium placed in air, then ray after emergence of that medium, there is a shift in the uh, incoming ray, and this shift is called lateral shift. For example, this is a glass, and if ray is passing through this glass, then when it will emerge from the glass, there will be shift in its original path, and this original the distance between original and emergence path will be called lateral shift. As shown in here, we are seeing in this picture a ray is passing through like this. This is the air and this is the glass, and when it enter into the glass, it went toward the normal because glass is denser than air, and when it comes out of the glass, again it went away from the uh, normal, and the final path of ray is this. And now initial path of ray is this. If there is no glass, the ray will go directly flowing this path, but the path have changed due to the placement of glass in the path of ray, and this is a lateral shift. Now we have to calculate this distance, lateral shift distance. So we will use science law to calculate this distance, that is lateral shift. In figure here, CD is lateral shift. This distance is called lateral shift. That is the perpendicular distance between emergence ray and the uh, original path of ray is called lateral shift. You can define it like this. Now in triangle ABC, here this is the A, this point is B, and this point is C. In triangle ABC, cos R1 equals to base by hypotenuse. So AB by hypotenuse, here this angle, in this angle hypotenuse is AC. So AB by AC. This implies AC equals to AB by cos R1. This is equation 1. Again in triangle ACD, this is the triangle ACD. Sin I1 minus R1, sin I1 minus R1. This is the I1 minus R1 angle. This angle is I1 minus R1. So sin I1 minus R1 will be CD by AC. CD by AC, because this is the perpendicular and this is the hypotenuse for this angle, and so CD by AC. This implies CD equals to AC sin I1 minus R1, and AC. Now we have calculated the AC of value from 1. So putting the value of AC from 1, we get AB by cos R1 into sin I1 minus R1. And so that is CD equals to, CD is the lateral shift. So CD will be, and AB is the thickness of glass. So, and if it is represented by T, then we can write CD equals to T sin I1 minus R1 divided by cos R1. This is the relation between lateral shift, thickness of the glass, and angle of incidence and angle of refraction. Now some phenomena related to refraction. We will discuss about the phenomenon related to the refraction. For example, the bottom of a tank appears to be raised, and this can be explained with the phenomenon of refraction, that is here it is shown in the figure. For example, consider a object is placed in the bottom of the tank, and tank is filled with water or any material which refractive index is greater than air. So this medium will be of denser medium, and the air will be of a rare medium, because our eye is in air. So when light passes through denser to rare, we know that it bends away from the normal. Here this is a object, point object. Now if we consider this ray is passing, we have to take one ray passing normally, so it will not deviate, because we know that any ray passing normally does not get deflected. So if one ray is passing like this, so it will be undeflected, but obliquely passing ray are deflected by the uh, rules of reflection. So when this light goes and comes out from the tank, because it is passing from denser to rare medium, so it bends away from the normal. Now this is the normal, so the original path will be like this, but due to coming from denser to rare medium, it bends away from the normal, and so ray will go in this direction. Now uh, when we now this ray looks that it is coming from the point O dash. So our eye will experience that the point is at this point. So so the bottom of tank is appears to be raised to our eye. This is the explanation of this phenomenon, and you can also calculate mathematically the that is the height of raised bottom. Now in triangle BOC, here BOC, sin I equivalent to tan I, because I is very small. So OC by BC, OC by BC equals to OC by S2, because we have taken the thickness of tank as S2. This is equation 1. And now in triangle BO dash C, this is the BO dash and C, BO dash C dash, sin R equals to tan R equals to O dash C dash divided by BC dash. So we get O dash C dash by H1. This is equation 2. Now from Snell's law at B, we know that N1 sin I equals to N2 sin R. So this implies sin I by sin R equals to N2 by N1 equals to N21. This is equation 3. So from dividing equation 1 by equation 2, we get sin I by sin R equals to OC by S2 into H1 by O dash C dash equals to H1 by S2, since we have OC equals to O dash C dash. And from 4 and 3, H1 by S2 equals to N21. This implies H1 equals to S2 into N21 equals to S2 by N12. Hence, apparent height will be equal to the true height divided by refractive index of the first with respect to second. If the second medium is air, then N12 equals to N1 air equals to N1 equals to N, say, then apparent height will be true height divided by refractive index of first medium, that is or H1 equals to S2 by N. where n is the refractive index of the material placed in the tank. Now advance sunrise and delay sunset. Now this can be also explained uh, using the phenomenon of refraction. For example, consider this is our earth and a man standing on the earth seeing the sunrise. Now light, because earth is a the earth environment can be considered made of many layers with different refractive index, and the refractive index of atmosphere increases towards the, that is uh, the refractive index increases when we come uh, go towards the earth's surface. So light from sunrise enters from rare to denser medium at every point. So when light is coming from the sun, it means that it is entering the from rare to denser medium. So it always bends towards the normal. Now, for example, here it bends toward, this is the normal for this layer. So this will bend, original path will be like this, but due to bending, this will go in this way. This is the second layer. Now original path will be like this, but due to bend, it will, light will pass through this, and similarly will get deflected at every layer and finally reaches our eye. So we see the, when what we see, because light travels in a straight line, so it appears that the light is coming from this point. So Earth original position is at this point, but it looks that the sun is sun original position at this point, but it appears us that sun is at this point. That is, this is the apparent position of sun. Now next topic is our critical angle, and it is written as IC. Here two medium is a boundary is drawn between two medium, that is medium 1 and medium 2. Now medium 1 is denser N1 with refractive index, absolute refractive index N1, and the second medium is rarer and with refractive index N2. Now let us see if we light incidence on the boundary of the separation, that is light passing from one medium to another medium, and here this is denser and this is rare. So when it comes out from the medium, denser medium to rare medium, it bends away from the normal. So this is the normal, so it will go like this. Now this bending, if we increase the angle I, the bending will also increase, and a time reaches when the light passes parallelly to the boundary surface, that is the angle of refraction, angle of refraction becomes 90 degree, and this condition, at this point the angle of incidence is called angle, critical angle. So when light goes from denser to rare medium, it bends away from the normal. The maximum angle of incidence for which the refracted ray makes angle 90 degree with normal is called critical angle. Now from Snell's law, sin I by sin R equals to N2 by N1 equals to N21. This implies N1 psi equals to N2 sin R. For I equals to IC, that is critical angle, when angle of incidence becomes critical angle, R equals to 90 degree. Hence, N1 sin IC equals to N2 sin 90. This implies sin IC equals to N2 by N1 or N21. This implies sin IC equals to 1 by N12, or sin IC equals to sin inverse 1 by N12. This is the formula for critical angle in terms of refractive index of first medium with respect to second medium. Yeah, we can say that the refractive index of denser medium with respect to rarer medium. If the second, that is rarer medium, is air and the first medium, denser, is a medium of refractive index n, then the formula will be IC equal to sine inverse 1 by n.